you the floor.
Thank you very much for the invitation. Sharing the screen, so you should be able to see my screen now. Yes, thanks for having me in Leuven. Would be great to be there and have some Belgian beer after the talk, that we'll kind of do without for today. So as Joris said, I'm interested in anything that has to do with white dwarfs, and I selected a topic today which I call Dance of the Death in the Planetary Graveyard, and it all has to do with what happens to planetary systems when their host stars become white dwarfs. Just need here to set up something for a second. Okay, right. This is the overview outline of my talk. I will briefly summarize what happens to planetary systems once the host star evolves off the main sequence. And then I will tell you how we find evolved planetary systems. And one exciting aspect is that we can use those to measure the bulk abundances of exoplanetesimals and by analogy of exoplanets. And then finally, I will talk about actual real planets going around white dwarfs. So first part, the late evolution of planetary systems. So we now, after about 25 years of studying exoplanets, that kind of within astronomical precision, every star has planets. And here's just an example. This is not the solar system because there's a nice water world, which is the fourth planet. So this is just an artist's illustration. But the questions that I will address today is like, what's the future of these planetary systems? And what is the future of the solar system? And what can these systems actually teach us? Let me try to get rid of that little gray bar up there. Okay, I have to live with that. Okay, so just to shape intuition, let's have a look at the solar system. This is the configuration as it is today. We are here on planet number 3. We have 4 rocky planets. We have an asteroid belt, and then we have giant planets further out. The sun is currently halfway through its evolution, 4.5 billion years, and another 4.5 billion years roughly it will evolve into a red giant, grow, and then become a white dwarf. So what will that do to the planetary system? The sun will become roughly an astronomical unit in radius, so it will reach up to where the Earth is now, and it will definitely evaporate Mercury and Venus. But because it loses half of its mass in the process, everything that orbits the sun moves out by factor 2. You can see that if I flip back and forth, the orbits of the planetary planets and planetary bodies grow by about a factor 2. So whether or not the Earth might just escape evaporation isn't totally clear, but it's not really relevant for what follows in the talk. Conclusion is that in 6, 7, 8 billion years from now, the solar system will contain a white dwarf in the center with roughly half the mass of the sun of today. It will have a terrestrial planet, asteroids, and the giant planets further out. So there will be large parts of the solar system that we have today intact, orbiting a white dwarf. Now, this is true for other exoplanetary systems. Here are 2 beautiful images of exoplanetary systems. This is HR 8799. This is kind of poster child of direct image planets. You've got 4 planets, B, C, D, and E, orbiting an A-type star, and that's Beta Pig, the planet going around another A-type star. These stars have masses of 1.5 and 1.75 solar masses, and they will become white dwarfs very soon in kind of astronomical timescales, a couple of gigayears. Then they will become white dwarfs, and those planets will survive the evolution into the white dwarf stage, and these will make white dwarf planetary systems. Now, if we look at the distribution of exoplanets that we know, a lot of them have been found by design around solar type stars, but we know planets around stars up to a few solar masses, and then now also down into the low mass red dwarfs. And all these planet hosts will eventually become white dwarfs. The M dwarfs take a little bit longer, but in the future, all planet hosts become white dwarfs. And for the purpose of this talk, we just go over here and end up on the white dwarf cooling sequences. White dwarfs are born hot, and because they have no longer nuclear fusion as a power source, they just eternally cool along this white dwarf cooling track. Now, just to keep it a little bit interactive, if we think about how can we actually identify evolved planetary systems. Going back in the history of observational astronomy, when do you think was the first observational evidence for another planetary system obtained? I just say the data was obtained. It wasn't correctly interpreted at the time, but it was obtained. And so I know that most of you are muted, but maybe you can type it in the chat, or Joris can unmute you. Just a quick guess.
Yes, if anyone has a guess, please unmute yourself. So
late 90s, I would say.
Yeah, people
Late
suspect
90s.
it to be wait, someone is doing a guess. 1992.
92. That's a very good guess. That was when the pulsar planets were discovered. Okay. If there's no further guesses, I'll reveal the answer. 1917. So more than 100 years ago. I come back to I will show you the actual data, but to understand why that data flags up a planetary system, here's a very, very quick one-slide overview of what you need to know about white dwarfs for this talk. White dwarfs are the burnt out stars, burnt out cores of stars like the sun. They are roughly Earth-sized. They have order of half the solar mass. And in this diagram, you have a cross-section through a white dwarf in log mass. Okay, so this is a log scale. 99% of the white dwarf is down here, and that's carbon and oxygen. That's the ashes of hydrogen and helium burning. And then you have some residual helium, and in most cases, some residual hydrogen floating on top. So the atmosphere is up here. And if we observe a white dwarf, then we expect to see a spectrum that is pure hydrogen or pure helium, or maybe a mixture of hydrogen and helium, but we expect no metals, nothing heavier than hydrogen or helium, because of the strong gravity. All the metals settle down out of the atmosphere, so we won't see that. Here's the actual data. That is a photographic plate. It's a spectrum. The star is the spectrum in the middle, and then you have kind of comparison lumps, calibrations to either side. And the feature that I'm talking about is this here. This is a negative. So there are two absorption lines in the spectrum, and that's the calcium H and K doublet. This data was obtained by Van Maanen at the Carnegie observatories. He was studying high proper motion stars and observed this star, which is now called Van Maanen 2, which has a proper motion of 1.4 arc seconds per year, so a really fast moving star. Then you obtained a parallax, and the distance to the star is 4.4 parsec. And here you have a modern spectrum that's obtained with the ESO VLT, with the UV spectrograph. You see calcium, magnesium, and iron absorption line. Now, back then, people didn't know much about white dwarfs, and he thought it's an F star because F stars have very strong calcium H and K lines. But given the parallax and the apparent magnitude, it became clear that that's a very weird F star, and he called it the faintest F-type star known at present. So, but it's not an F star, it's a white dwarf. It was the third white dwarf to be discovered, and it has metals in its atmosphere. Now, I mentioned before that white dwarfs quickly stratify chemically, and I will illustrate that here with a little movie. So at any cooling age of a white dwarf, the time on which metals settle out of the atmosphere is short compared to the cooling age. What you will see in this movie is the actual data of a white dwarf. That's the gray line with very, very strong absorption lines of metals. Red is a model atmosphere fit. You've got time 0, that's today. And then you've got here the calcium over helium abundance, that's that red dot. And you have a color diagram because actually the color of the star changes. Okay. A little bit fiddly to get. It's a little bit fiddly to get the laser pointer off. Okay. Right. Okay. So Now I switch on the movie, keep an eye on the clock, top right. That's 1,000,000 years. You see the calcium abundance is dropping and the lines become weaker. And I'll try to stop the movie now-ish. So after 2.5 million years, the spectrum resembles that of Van Maanen, the star that I shot on the previous slide, with pretty much just very strong calcium H and K lines. Okay, so within 2 million years, 2.5 million years, the metals are almost gone. This star has a cooling age of several giga years. So compared to the age of the white dwarf, the metals disappear almost instantaneously. And that means if we see metals, they must have been dropped into the atmosphere very, very recently. So the question is, where do these metals that we see in Van Maanen star come from? And that takes us into the second chapter, dust disks. So in 1987, Ben Zuckerman and Eric Backlund, they were using one of the first infrared detectors, and they were searching for brown dwarfs. So brown dwarfs weren't found back then. They're the substellar objects that never reach hydrogen burning. And they had this idea that rather than just looking for brown dwarfs somewhere in the field, they thought it's easier to look at stars and look for a brown dwarf companion. And they favored white dwarfs because white dwarfs are faint by themselves. So if you look for a faint, even fainter brown dwarf companion, the contrast ratio is better than looking at main sequence stars. And they discovered an infrared excess at this white dwarf called G29-38, which you see here. The blue data is a spectrum obtained by the Spitzer Space Telescope, and the infrared excess. So what do I show here? This is the white dwarf spectrum, the optical wavelength range. This is the infrared. That's the infrared excess from of the white dwarf, and then this feature here, that's actually silicate dust. Right, now you may ask the question, why should there be silicate dust around the white dwarf? And people who model dust fitted that feature and say it's olivine. Olivine is a silicate compound. And we have olivine on Earth, for example, this green beach on Hawaii, that's olivine. So how do you get dust around the white dwarf? The whole story kind of fell together in a kind of coherent picture by a seminal paper of Mike Jura in 2003, where he postulated that planetary systems survive into the white dwarf stage. And if you have an asteroid that gets too close to the white dwarf, it will be tidally disrupted and then shredded into dust and form a disk of dust around the white dwarf and eventually accrete onto the white dwarf. So the paper by Zuckerman and Backlund was published in 1987 in Nature, and this is just a little story for the younger people in the audience. If you publish, usually you would think you publish a paper in Nature and it's great and you're kind of on the way to become famous and get a job somewhere. But then papers are judged by citations, and you see here, this is the citation record, and it's dropping to single-digit figures very rapidly. And if you had written that paper, you would be quite disappointed, but then sometimes things happen. Spitzer was launched, and so this single white dwarf with an infrared excess suddenly became just the prototype of a very large number of systems. And since then, citations have rocketed up, and this paper has now something like 300, 350 citations. So never give up, even if your paper at some point doesn't seem to attract the impact that you hope. Now, how do you get planetesimals, asteroids, small things, onto an orbit that brings them close to the white dwarf? This happens actually in the solar system. On the left-hand side, you have a movie taken with SOHO. This is the sun, where the sun is hiding behind this coronagraph. The white radius shows, the white ring shows the size of the sun. And to tidally disrupt, you need to bring an asteroid to within about 1 solar radius of a white dwarf. Okay, so what happens in the solar system? We see that comets or asteroids, most of the time comets, are sun grazing, so they get very close to the sun. They get to where, if the sun was a white dwarf, they would enter the Roche lobe. And you can also model the evolution of planetary systems as an n-body simulation, which is shown here. You have a planetary system on the main sequence. It goes through the giant branch, and then during the white dwarf cooling stage, you develop gravitational instabilities that nudge planets around and kick some of the, even some planets, not just asteroids, planet-sized objects, very close to the white dwarf, with Roche radius being down here. Right, so one step further, this is when kind of we accidentally entered into this area without actually planning to do so, gas disks. Back then, we were studying white dwarf binaries and sifting through a large number of spectra from the Solar Digital Sky Survey, and I came across this spectrum, which has double-peaked emission lines of calcium over here, and then it has some iron lines, and it has a magnesium absorption line. And it turns out that you get double-peaked emission lines if you have a flat disk of gas that emits in lines. And the reason is the Doppler effect. If you're an observer, then you see material both moving away from you and approaching you. And so you get a double-peaked line profile where the shape is determined by the velocity structure in the accretion disk. Now, we kept observing this specific star. Let me just go back for a second. So the elements in the disk around that star are only metals, so iron and calcium, and we see magnesium in the atmosphere of the star. There's no hydrogen emission lines, and there's no helium lines, so there's no hydrogen or helium in the disk, and that's why we concluded this is a debris disk of planetary material. Now, we kept monitoring this star over quite a number of years because it was just kind of such an unusual thing. And we started to notice that the shape of the double-peaked lines changes on the time scale of years. You can see it's kind of nice, symmetric over here, 2007. And then the profile becomes very asymmetric with a sharp spike at blue shifts and a stretched shoulder at red shifts. And we applied Doppler tomography and could turn this sequence of spectra into an image. It's an image in velocity coordinates, so it's a little bit different from a coordinate-based image in the sense that it shows velocity in the gas, and because it's Keplerian, Kepler's law implies that velocities get larger as you get closer in. It means that the inner edge of the disk is the outer circle here, the highest velocities, and the outer edge of the disk is at lower velocities, is on the inside in the velocity diagram, but it shows a very, very well-confined asymmetric distribution of intensity that creates this pattern. Now, it's a little bit abstract, but I can illustrate that with a movie. Imagine you have your telescope up here and you observe the disk, and you will have material that moves towards you and moves away from you. So let's assume that the material here moves downwards. You are the observer up here. So at that moment in time, this material would move away from you. You would see the intensity redshifted because most of it is parallel to your line of sight. You would get a very large spike on the red side of the profile. Now let's switch on motion. And you see as the material moves around, the profile changes. And if I manage to stop it, which is always a bit tricky, around here, you have this bright blob of material, which is still has a blue shifted component, so this peak is stronger. And then as it moves around, you will have zero Doppler shift, and the profile will become symmetric. So this is a very short animation that illustrates how Doppler tomography works. The curious thing is that the precession, the period on which this profile changes is 25 years. The orbital timescale within this disk is hours. Okay, so it takes just a few hours to go around the white dwarf if you're within a solar radius. And yet the pattern changes over 25 years in a very stable fashion. And I will come back to that in a second. Just to put that into context, debris disks are actually kind of omnipresent in the universe. This is a debris disk of some small planetesimal or moon or something that got too close to Saturn and got disrupted and formed the rings around Saturn. And to scale, you've got Saturn here, and this is the disk around the white dwarf that I was just describing. So we can move on from disks to actual planetesimals. So we kept on observing this same star with the gaseous debris disk. And we wanted to probe if there are signs of flickering or ongoing accretion or some short-term variability in the disk. So we observed the system for 5 nights with the GTC and obtained about 2 minute spectra for long stretches of time. The average spectrum of the line profiles is shown up here. And then The middle panel is what we call a trailed spectrum. So you've got time or phase, as I come to in a second, going in this direction. And the bottom panel is the middle panel with the average profile subtracted. And so once we subtract the average profile, we see that there is a very small change in the morphology, shape, and intensity of these emission lines that we see both in the equivalent width and in the blue to red flux ratio. And these variations occur on a period of 2 hours, 123 minutes, and they're stable over a period of 1 year, over a baseline of 1 year. And that means we have a stable clock in the system. And the only way we could explain that was by postulating that that corresponds to the orbital period of a solid planetesimal orbiting the white dwarf with a period of 2 hours. And simply based on the fact that an object survives that close to the white dwarf implies that it has to have either a relatively high density, at least 8 grams per cubic centimeter, which is density of iron, or it may have some internal strength. And we think that this is the core of a planetesimal that got disrupted. The outer layers formed the gas and dust disk that we see, and the core remained intact, is now orbiting the white dwarf. And we believe that this planetesimal creates the metallic gas and is on a slightly eccentric orbit that is precessing due to general relativity, which leads to the 25-year precession period that we see and the changing shape of the emission line. So here's an artist impression. You've got the debris disk, and you've got the former planet core that is orbiting within the disk, and via collisions creates the gas that we see. And similar things are seen in the solar system. So this is a Cassini image of Saturn's rings. This is Daphne, one of the little moons that orbits Saturn, and it opens up a gap and leads to some perturbations in the rings. Right. Now, when I gave talks about this science at exoplanet meetings, people were very skeptical, and they said, we want to see something more concrete, something more specific. And then exoplanet scientists like transits, because then you're really sure that something is going around your star. And the discovery of transits came 5 years ago by Andrew Vanderbosch. He discovered in Kepler data periodic dips in the brightness of a white dwarf, WD 1145, occurring every 4.5 hours. And then follow-up observations showed that this white dwarf has metals in its photosphere, so it's accreting planetary debris, and it has an infrared excess, so there's dust around the system. We started follow-up observations of this star, and here's high-speed photometry that spans one orbital cycle, and there's not just one transit, there's just a multiple sequence of stuff going in front of the white dwarf, blocking parts of the light. And we can work out some mass loss rate of the body that orbits the white dwarf, and we can figure out that the structures that block the light, these are not solid planetesimals, but these are large structures. These are dust clouds that are several times the size of the white dwarf. So we think something's happening like this picture of a comet here. We have a comet that becomes active and loses gas and dust that then blocks the light of the white dwarf. And these structures evolve over timescales of night. So this is a sequence of about a week folded over the orbital period of the planetesimals. And you can see structures appear, become stronger, and then fade again, and there's multiple of them. So we measure the periods of these different transits to a precision of a couple of seconds, and we find that all these transits have the same orbital period with variations of just a few seconds, and they're stable over hundreds of orbital cycles. It's like a necklace of debris going around the white dwarf. And we went then on to do n-body simulations of this system, from which we could conclude that the body that goes around and loses this debris has a mass of less than 10 to the 20 kilogram, which is like a large asteroid, and a density of around 3.5 grams per cubic centimeter. And it has to be differentiated, so it has to have a density gradient across its structure to maintain stable over the observed periods of time. So that was 5 years ago. It took 5 years to find the second example of a white dwarf with debris transits, which is shown here. And if you look at the plot, you would say, well, that looks very similar to the one you've just shown before. But the difference is the x-axis. So between two transits, we now have actually 110 days. And that is that's a very wide orbit. And that means that that body can't be on a circular orbit near the Roche radius. And we still don't quite understand how you get debris transits with such a long period. You probably need a very highly eccentric orbit that crosses at periastron into the Roche lobe radius. Now, one system, you can call it a freak. If you have two, it's a kind of a coincidence maybe, but once you have three, you have a small class and you can start to study statistics. Now, there is a third one. I'm not allowed to talk about it, but these systems exist in larger numbers, and well, I can say that the third one is nearby. It's 36 parsec away. So these systems are probably more widespread than we actually think. Very few words about bulk abundances, because I need that later on. What are planets made out of? Usually we would say, well, we go and we scratch the surface of Mars, or we fly through Gaseous of Europa to measure the abundances, but that never tells us the bulk composition of a planet. In fact, bulk compositions of planets, we learn that from studying meteorites. So that's bits of rocks that fall from the sky, and we can analyze them in a lab and then reconstruct what planets are made out of. And in the context of white dwarfs accreting planetary debris, we do exactly the same. We have planetary debris. It falls onto the white dwarf. Excuse me. We take spectra of the white dwarf and we measure the abundances of the debris. And here are two examples. These are two cool white dwarfs, pretty much same temperature. They have very different spectra because this one up here accretes a crust-rich fragment, so rich in calcium, titanium, sodium, whereas this one down here accretes a core-rich, something like an iron meteorite, and we see mainly iron and nickel lines. And that means we can then compare the abundances of exoplanetesimals to things we see in the solar system. This is a kind of a busy plot. What I do here is I show the abundances of debris accreted by white dwarfs in the different elements, normalized to the abundance of silicon. So silicon is 1 in that plot. And that ratio, I normalize it by the same ratio in the Earth. That may seem complicated, but all it tells us is that dots that sit above the dotted line are enhanced in the specific elements, and data points that sit below the line are depleted with respect to the average abundance of the Earth. Let me just skip that and go straight to the punchline. Within the uncertainties, the white dwarfs, which are all the colored dots here, are more or less consistent with things we see in the Earth crust, mantle, or core. And so the conclusion is that these white dwarfs accrete rocky planetesimals, fragments of leftovers of planet formation that resemble asteroids and the inner solar system planets. We can even detect water because minerals are always bound to water. It's metal oxides. So we detect all the metals. We can count up how much oxygen the metals bring. And if we see an oxygen excess, too much oxygen with respect to the minerals, then the only way to add oxygen is to actually have water. And that has been detected in a small number of systems where we can work out water mass fractions of 25 to 40% and parent body masses of 10 to the 22 grams, which is similar to Ceres, the largest body in the solar system, planetesimal in the solar system, that is thought to have a rocky core and a large layer of water, ice, and dust on top. This is very interesting in the context, how did we get water on Earth? Because the Earth actually is very dry. It just has a very, very small amount of surface water. And you only need seven objects similar to Ceres to deliver the water to Earth. Now, I don't say that that's how it went, but just to give you an impression of the scale of the problem of getting enough water to make a planet habitable. Right, into the last chapter, planets, real planets. So 2 years ago, we looked at a spectrum from the Sloan Digital Sky Survey again, and it's a white dwarf which has emission lines of hydrogen and oxygen and sulfur. And we had no idea what's going on, so we got better data with extruder on the VLT. In black is this new star. What we see is double peak lines, so we have a disk, but we see no metals. There's no calcium. This in gray is, for comparison, the disk system that I showed before. And we detect hydrogen, oxygen, and sulfur, and we see forbidden lines, which we usually don't see in accretion disks around white dwarfs ever, because that requires relatively low densities. So the only elements that we detect both in the atmosphere of the white dwarf, so there's material accreting onto it, and in the disk around it is hydrogen, oxygen, and sulfur. We have a disk around it, and that caused some head scratching. Okay, this slides are a little bit out of order here. So head scratching, I looked at textbooks and I came across this plot, which shows the composition of the deeper layers of atmospheres of the giant planets in the solar system. And I was like, oh, well, hydrogen sulfide, we see hydrogen, we see sulfur, we see oxygen. We don't see nitrogen and carbon, but we are not very sensitive to these two elements. So the idea was, well, maybe we're a planet that, a giant planet that is evaporating. Now, why would a planet around a white dwarf evaporate? That white dwarf is very hot, 27,000 degrees, so it has a large amount of extreme ultraviolet, and that drives mass loss from the planet. That is seen in main sequence, planets going around main sequence stars, where you have in the ultraviolet, the H-alpha emission from the star. So this is emission from the star. And on this side, the flux is suppressed because you have a evaporating planet that is transiting in front of the host star and blocking some of the Lyman alpha flux from the star. Now, the amount of evaporation, the key parameter is how much extreme ultraviolet flux you have. And something that then occurred to us, like so one of those months where you think, like, why did nobody think about that before, is that young white dwarfs are the most extreme ultraviolet luminous objects because they're very hot. Shown here is an HR diagram with the EUV luminosity coded, color coded on a log scale. So on the main sequence, the sun is a fairly feeble EUV emitter. It becomes a red giant, moves over here, and then the white dwarfs become visible with extreme ultraviolet luminosities of about 10 solar luminosities. Now, if you just go through the numbers, you will work out that EUV flux is sufficient to photo-evaporate, drive mass loss from Jupiter at 10 AU, because that's where Jupiter will be once the white dwarf, the sun is a white dwarf. And that means the sun, when it becomes a white dwarf, for some period of time, will drive mass loss from the giant planets. Okay, let me just go back. So the conclusion is, what we found here is a hot white dwarf that photo-evaporates a giant planet which orbits the white dwarf at a distance of something like 10 solar radii, periods of a few weeks. Right, now again, just things are moving fairly quickly. We have now the first transiting planet around the white dwarf, published in Nature last month, again by Andrew Vanderbosch, this time discovered with a test satellite. And he found a relatively deep transit in the optical. So that's the optical light curve over here. Then they observed the same system with Spitzer in the infrared, and they find that the transit depth is the same in the optical and in the infrared at 4.5 micron. And from that, they conclude that it must be a very cool, basically dark body that orbits the white dwarf that has a very low surface temperature. And the only thing that comes to mind is a planet, because even a brown dwarf would be detectable as a color dependence in the transit depth. The conclusion from the paper is that the object has a mass of less than 14 solar masses. The eclipse is only grazing, so it's a little bit tricky to determine exact parameters, but the orbital period is 1.4 days. And yes, so radius is of the order of 10 solar radii. So the best guess at the moment is that this is a giant planet with borderline giant planet between planets and brown dwarfs. The white dwarf itself is unspectacular. It's cool, 4,700 degrees. It doesn't have metals in the atmosphere. It doesn't have an infrared excess. And if Tess hadn't looked at that star, we wouldn't know that it has a transiting planet. The one thing that is exceptional about that white dwarf is that it is really nearby, distance of 25 parsec. And that means that close-in planets around white dwarfs are probably much more common than we currently think. We just haven't looked in all the possible ways to find them. And that brings me to the end of the talk. Basic summary, very quick summary, is that planetary systems around white dwarfs are as common as they are around main sequence stars. That's not a big surprise because a lot of the planets will just survive the evolution into the white dwarf stage, but it's something that wasn't intuitively clear until a few years ago. And besides being pretty exciting to think about that even in the solar system, planets will survive into the white dwarf stage, we can use this system, among other things, to measure the bulk abundances of exoplanetary systems and how frequent we have water. And we can probe the architectures of planets around A and F type stars, which are the progenitors of the white dwarfs. Okay, nice stop here.
Thank you very much, Boris, for a very nice talk. Thanks. So there might be some questions. If you have a question, put your name in the chat, and then I will call you, and you can ask your question to Boris.
Maybe I read the share screen share. Okay.
Very nice movie, of course.
Yes, that's done by ESO. They have quite good people.
Hans, you have a question, please.
Yeah, thanks for the talk. I have a question with respect to the evolution of those systems, because the white dwarf was once an AGB star, and the orbits that you quote for the planets is must have been, well,
yes,
almost within the AGB. Well, I mean, so
yes.
What is the orbital? Can you recompute the orbital evolution of those planets? And then a second question I have: these are first generation planets, I suppose.
Okay, so first, the first question.
Yes.
That's a very, very good point. I skipped over that. So
yes.
this planet here at 10 solar radii would have been basically deep inside the red giant.
Yes.
And so it's clear that that planet cannot have been where it is today when the
yes.
star was on the red giant branch. And there are at least two possible ways to get a planet from further out, which means beyond beyond 1 AU, let's say, order of 1 AU, to get it close in. One is common envelope evolution, so that the planet just enters the red giant envelope shortly before the envelope is unbound anyway, and then it gets dragged into the envelope, and the orbital angular momentum and energy helps unbinding the envelope, and that as a side effect, the planet gets drawn inwards. That's a fairly small parameter range that is where this is possible, because planets have such a low mass that if they enter the envelope too early, they merge into the white dwarf. They just get dragged right down into the star. So that is a possibility. And the other one, which we favor for this system here, is that you have a multi-planet system, and that you have gravitational interactions between the star. And I had a slide on that. So if you have multi-planet systems, then you get gravitational interactions between the planets. So this is an n-body simulation of 10 planets, which are tightly packed on the main sequence. And then the orbits widen through the giant branch, and in the white dwarf cooling stage, you get gravitational instabilities, and some planets get nudged onto eccentric orbits that take them close to the white dwarf, where then tides can circularize the orbit onto a short, close orbit around the white dwarf. And just remind me of the second question.
Well, the second question was because we are interested in the second generation of planets. But
yes.
Yeah, I don't know how you. So the NNSER system.
Yes. So that's a really good question. For the kind of these two planets, they're giant-sized planets. I don't think they can form as a second generation. There's just not enough material around. But even for the rocky asteroid-like things that we see, in a single star, you would typically think that mass loss is spherical or order of spherical, and you probably don't reach enough densities to form second generation planets. But you mentioned Anna and Sir, so in a binary system,
Yes.
you have an axis of symmetry, and you can capture some of the mass lost from the star in a circumbinary disk, where then you have much higher densities and may form second generation planets in the circumbinary disk. So there I think it's possible, but around single stars, I think second generation is difficult, also because the white dwarf keeps its space velocity and leaves the birthplace where the planetary was relatively quickly.
Yeah. So whenever we see disks, it's always in a binary in the post-EDB stars.
Yes.
So there. Yeah. Okay. Thank you.
Thank you, Hans. Does anyone else have a question? I actually have one myself, if I'm allowed, of course. What's our? I mean, so you're conducting surveys on white dwarfs. What's our idea of the white dwarf completeness? Should I phrase it? So, what fraction of white dwarfs in the not too distant radius from the sun can we detect with spectroscopy? Have you any idea on those numbers?
Yes. So that's a good question. Until pre-Gaia, it was very, very difficult to find white dwarfs because they're so small, and once they cool down to 6,000 degrees, 5,000 degrees, they have the similar colors to G and K type stars, and they're very difficult to pick out against more distant background stars. And in the past, proper motion was the only way to distinguish. With Gaia, you have the distances, so you know the absolute magnitudes, and it has become trivial to identify white dwarfs. And so pre-Gaia, we had a complete sample of white dwarfs within 20 parsec. That is about 120. That used to be about 120, 130 white dwarfs. With Gaia, we can push out to about 40, 50 parsec. But the coolest white dwarfs, they reach Gaia's magnitude limit of around 20th magnitude at about 50 parsec. And so we have just completed the spectroscopic follow-up of all white dwarfs within 40 parsecs in the northern hemisphere, which is about 600 stars, and we are close to finishing the same in the southern hemisphere.
Okay, very nice. Anyone else? A question? Cool, please.
Hi, thank you. That was a wonderful talk. I have a question about the pulsation properties of these white dwarfs.
Mm-hmm.
So as white dwarfs evolve, their pulsation properties change. Mm-hmm. Is that does the evolutionary changes to the pulsations have more of an effect than, say, anything that might temporarily be introduced because of the sudden increase in local metallicity?
Yes. So the pulsation properties of white dwarfs remain, as far as I know, unaffected by accretion of debris or not. In fact, the prototype system that I showed, this one here, this white dwarf is a ZZZ pulsator. So this has a hydrogen envelope, hydrogen atmosphere that is currently driving non-radial pulsations. And as far as we can tell, the fact that there's a small amount of metals in the atmosphere doesn't make any change to it.
Okay, and just a quick follow-up, if I may. Mm-hmm. Have you tried looking at these with the pulsation timing method to derive time delay curves and radial velocities for the planets or for the white dwarfs themselves?
Yes. So J.J. Hermes has some conference proceeding on that. And he had a small number of white dwarfs where the pulsations are stable enough that you can track them over years. And he had some upper limits on, like, he had no detections of timing delays. And he converted that into upper limits on the planet masses. But that was just a handful, and the main problem is that not many white dwarfs have sufficiently stable pulsations. They're a little bit messy still.
Okay, thank you.
Okay, thank you, Cole. Anyone else have a question? Yes, please, Dominic.
Hi, Boris. Thanks for a great talk. When I look at the light curves, they remind me of a Kepler object called Tabby's star.
Yeah.
I'm just curious if you can draw any parallels between this single object on the main sequence, which has these irregular aperiodic dips in its light curve.
Yeah, that's a good point. The answer is I don't really know. I think we know more about these white dwarfs, transiting white dwarfs, than we know about Tabby's star, because here we are really confident that these are periodically reoccurring events. With Tabby's star, I haven't followed it, what the current idea is, where the material is that causes the transits, and what the origin of that material is. But you're right that the shape of the structure looks quite similar.
Yeah, I'm also a little out of date on Tabby's star, maybe a year or so, but I think the latest one is some sort of dissolving exomoon or something that is slowly causing disruptions. But yeah, it looks remarkably similar, but that's only 1 in a million compared to your beautiful white dwarfs.
Yeah, that's true. There is also a handful of very short period planets around main sequence stars that are disintegrating or disrupting, that have similar shaped light curves, asymmetric transits, which again they're very close to the Roche radius and are losing large amounts of mass. So the morphology may be just similar for all these cases.
That's great. Thanks.
Okay. Also, Robin has a question.
Hey, thanks for the very interesting talk. I was wondering if it is possible for some of these planets to still retain their atmosphere, or is the evaporation too efficient for that? And maybe also, if the white dwarf is older and the radiation drops down a little bit, if it's possible for these planets to possibly reaccrete an atmosphere.
Another good question. I'm a little bit hesitant to answer something because I don't really know the answer. I can only speculate. For the giant planets that we have, for the 2 giant planets, their mass, they're basically gas giants, and so the mass loss integrated over the time when the white dwarf is sufficiently hot to drive mass loss is actually very small. So these planets, they don't lose large amounts of their total mass. If you had Earths or super Earths with a thin atmosphere that undergo the same process, they might lose all of their atmosphere. But then the question is, they might reaccrete water-rich bodies that bring water to them and kind of bring oxygen and hydrogen that might form a new generation, a 2nd generation atmosphere. Or you might have atmospheres from outgassing of the planet. So yes, I think there is a potential for rocky planets going around white dwarfs having a 2nd generation atmosphere. But that's very speculative. Nevertheless, there are papers already where people talk about habitability of planets around white dwarfs because they provide a nice long-term stable luminosity. Once you're in the range 5,000–6,000 degrees, you have something that has the same temperature as the sun and remains stable in luminosity for a couple of billion years, and you don't have the stellar flares that M dwarfs have. So you could potentially have, at least on paper, the conditions for habitable planets around white dwarfs.
All right, very cool. Thanks.
Nice. Anyone else have a question? If not, I would like to thank Boris again. Thank you very much for this very nice talk. Don't run away. So we tricked Boris into a coffee break.